Yep, okay, we're good to go. All right, sorry for the technical difficulties, everybody. Just wanted to flash the posters up here. So we got a really nice cast of characters for Tuesday and Wednesday. So make sure you check out the poster sessions tomorrow. We have lots of really exciting abstracts there, as well as Wednesday. So just wanted to highlight these talks here.
All right, excellent. Thank you, Vincent. Jason, you wanted to say a couple words before we get to the first talk.
Yeah, so, first I should apologize for in the first session only advertising the kits posters. I produced the PowerPoint at the last minute, so I will also show the reconnection posters very shortly. But I just wanted to reiterate one thing. Instead of going through all of the questions that we can ask about substorm onset, I think one of the main motivations of this session and the previous that we'd love anyone to address is how can we make concrete progress on the question of onset amidst proliferating theories and fundamental disagreements about causal pathways. It seems like we at least roughly agree on the phenomenological definition of onset, so that seems promising as a starting point. And here again are the poster sessions for kits. Well, it's the same poster sessions, but those are the posters. And here are Tuesday's reconnection posters. And Wednesdays. And so that should have all of the different posters advertised. All right, so yeah, let's get started. We've got tons of interesting talks. So.
All right, the first talk is Andy Marshall. Nice, okay.
So what I see is what goes here.
Cool. There you go.
All right. Wow, that is a bright light. Well, hi everybody, I'm Andy Marshall. Looks like everything's good up there. Unfortunately, a bit of false advertising here. I'm probably not going to actually get to talk to about the second event. So sorry to E, that's your event. And I saw Tony earlier. It's also going to reference one of his papers. But I think this is actually also my first time giving a talk at GEM. So thank you, everybody. Again, Andy Marshall, thank you for coming. I am an MMS baby. I've mostly been working on electron scale physics using MMS. So of course, I'm starting off with MMS observations. We have an event on July 3rd, 2017 that Li Jianchen reported 3 different EDRs with different guide fields. And Kevin Genestrati was looking at this more from what exactly is happening at reconnection onset out in the tail. So we talked about reconnection onset and substorm onset in the last session a little bit, and that's kind of what we're getting into. So what we are seeing, do I get a laser point, or can we see anything? Okay, well I can see it up on the screen up there, but not on mine down here. That's all right.
I should also mention I'm not seeing the slides online.
You are not seeing them online.
Okay, neither am I, yeah.
That sounds important. But they are on Zoom?
I'm not seeing them on Zoom.
Okay, I'm going to share my screen. No.
Nope. Fractal share.
Okay. Guess I crashed everything, my bad. So, how was everybody's traveling coming here? I got stuck in Detroit last night, but my bag made it here.
There we go. Looks great online.
All right, cool. All right, cool. Glad everybody can see it now. So what happened in this event anyway was the first pane is we're actually seeing the dynamic pressure in the solar wind. And what Kevin came to the conclusion of is that this first pressure pulse, it kind of started a stretching and thinning of the current sheet, which was preconditioning. Didn't even hit the next, okay. So that when another pressure pulse hit, it actually caused a collapse in that current sheet, and we got electron scale reconnection. MMS was out at about 20 RE tailward of Earth, so this is about where we'd expect to see a near-Earth neutral line forming. The thing is, though, that we didn't actually see a substorm happen. So this is kind of getting into that onset question, is does the reconnection actually make a substorm happen? Well, not necessarily. So Kevin identified this pressure pulse as being the trigger, and I also noticed when I started looking into this that we had a BY and BZ change, so a rotation in the IMF, and I have seen in the literature that people have talked about this extensively as far as changes in the IMF orientation causing a substorm, or in this case, a pseudo breakup. I'm just going to point out that this response at that time at 5:30 was pretty minimal. I've seen a lot in the literature that they use 100 nanoteslas in the AL index as the cutoff as to whether it's a substorm or not, or if they're looking for a statistical study. At that point, it does not have that. I looked at the SML data too, and it shows absolutely nothing happening at that time. Going to come back to what's happening closer to 6 o'clock, but at 5:30, when we saw the reconnection onset, there was nothing. So I also do a little bit of dabbling in global MHD modeling, so that's what we're going to be looking into for the rest of this presentation quick. I was looking at, first off, was there a big plasmoid ejected? Because if we see a near-Earth neutral line forming, it's supposed to eat through those closed field lines and eject a plasmoid. And then we're also supposed to see earthward traveling plasma and this substorm current wedge with an AL index, which I already said we don't have. So getting right into it, MAGE model. What does it show? Well, at 5:30, when MMS saw this X line forming, we definitely saw a current sheet. This is the bright red color here is the JY, crosstail current, and it shows there's probably an X line. It looks an awful lot like an inflow and diverging flows earthward and tailward at this point a few RE earthward of MMS, which I have also found out recently is pretty common in global MHD modeling. It puts the X line closer to Earth than it actually is. So that's actually okay. That's good. The other point is that these are all on closed field lines. The red field lines are closed. They are connected to Earth in the North Pole and the South Pole, which is a sign of a pseudo breakup, not necessarily a substorm yet. So everything is consistent so far. I also looked at the Bats or Us, the SWIMF model, and it's showing something pretty similar. So MMS is this red dot. The red field lines connected to the North Pole and the South Pole are all pretty much all we see in that area. So sounding like a pseudo breakup. So I got really curious, like what is going on out here at 6 o'clock? If we saw a reconnection, but we didn't see any substorm onset earlier, well, if 100 nanoteslas is one of the signs we use to see if this is a substorm, I kind of want to see what's going on. Maybe about 5:45 when that AL index starts to increase. So looking again at MAGE, I actually really cherry-picked the second plot. Again, 5:30, all closed field lines. 5:45, these lime green field lines are actually open field lines, which are connected to one pole and not the other. So that reminded me of this Chris Russell paper from 2000, where he looked at a two-point model, and he was saying when the near-Earth neutral line eats through all these closed field lines and gets to the lobe open field lines, that's when a substorm onset is going to happen. So that's what this puts me in the mind of. I am saying this to say that it is at least plausible that that's what's happening. But as you can see over the entire hour, there really isn't a plasmoid forming and getting ejected. So nothing really exciting like I would expect to see in a substorm. So I'm still not completely sure, but I can tell you about an hour later at 6:45, there again are only open field lines. The closed field lines just, well, they're not there. Something has happened. I also, again, was looking at the SWIMP, the Bats or Us model, because I thought, if we're looking for a plasmoid forming, maybe closer to 545 when the AL index starts to increase and the SML index starts to increase, maybe I'll find one there. And I have had good luck finding flux ropes, mini plasmoids with this model. And I do actually see on lime green field lines that there is some sort of a flux rope or mini plasmoid forming across the tail, but only partway across the tail. So that could explain why this is not a huge substorm with an AL of like 800, only barely breaks 100. So that is an idea, and I'm sure people have ideas about that. One last thing I'm going to show here is that at 5:30, this is the red color here is showing earthward flows. This is an isosurface where Bx is 0 right in the center of the plasma sheet. At 5:30, we can kind of see that where Vx is 0, it only moves tailward right at this one little spot where there's a fast earthward flow. So I would say that that is very possibly a sign of pseudo breakup, just more localized, short-lived, not across the entire tail. But by 6 o'clock, we can see also that this entire cross-tail Vx equals 0 has expanded in the y direction, and the earthward flows are a lot faster. So that also would be something I would expect to see with this higher AL. I noticed in the other event I looked at that was also the case. The cross-tail stagnation line, I guess I call it, is quite a bit longer. So I'm just going to leave it at that for now. And again, back to the MMS observations, it doesn't actually fully go into the lobe in this 5:30 to 6 o'clock time. It spends the time in the plasma sheet, and the plasma sheet boundary layer. I don't know how well you can see it, but this is the density right here. It gets down to about 0.1 per cubic centimeter, which is almost an order of magnitude larger than that girl's event, which was about 0.002, and that was definitely lobe plasma. So that is the other event I wanted to contrast this with, but in order to keep my presentation short today, thank you very much, everyone.
Are there any questions for Andy?
So I would highly encourage you to look at the ground-based data for your events to get an idea what these are, because by seeing reconnection or fast flow don't necessarily mean there is pseudo break or even substorm onset. Oftentimes what you see at PBIs or streamers, they happen all the time. Sometimes there are substorms followed after those events, but not oftentimes that's not the case. But if you look at oral measurements, you can make a clear distinction about all those things.
Okay, thank you. One question I have about that actually is that this event is in July, and isn't imaging rather hard to do at that time of the year?
Yes, in the northern hemisphere, but there are cameras in the southern hemisphere, so there can be chances of conjunction.
Okay, I will look into that. Thank you.
Okay, let's thank our speaker one more time.
All right. So again, thank you. If you got other things you need me to look at, I'm sure people in here know a lot more than I do. Happy to hear suggestions. Thank you.
All right, now we got to find out which one's yours.
Hopefully I put...
I do have it. Was it a PDF?
Oh, it might have been.
What's it called?
Probably something dumb like Gym 2025.
It wasn't I swear I downloaded it. Let's just get it again. Oh, yeah, you're right. Oh, all right, my apologies.
No worries.
There you go.
Cool. Is that sharing on Zoom?
Yes, should be.
Cool. Okay, hey everyone. I'm Harriet George. I'm a research scientist at LASP, and today I'm going to talk to you about a study I've been working on that's using multi-constellation observations of bursty bulk flows out in the magnetotail to try and figure out the cross-tail extent of magnetic reconnection. So most of the figures that we've been seeing in the previous session have been looking at the XZ plane of the magnetotail, the side-on view. But I want to take us into a different dimension, look at the top-down XY perspective to see how far across the tail the reconnection actually extends. And I've illustrated a couple of different scenarios here. So based on bursty bulk flow observations, the bursty bulk flows themselves are about 1 to 3 RE wide in the Y direction, which implies that the reconnection site that they originate from is also 1 to 3 RE wide. It's possible that there could be just one reconnection site active at a time, which I've got over here in scenario A. There's just one tiny wee baby reconnection site active at a time, spitting out one bursty bulk flow at a go. The other scenario is that there could be multiple spatially localized reconnection sites. I've got 3 in this diagram here. There could be 2, there could be 5. The important thing is that there's more than one. So with the multiple localized reconnection sites, you could have bursty bulk flows getting launched from different reconnection sites propagating through the tail. The third scenario is more of a global reconnection site. I've got this illustrated here going across the entire tail, but I would say any X line longer and wide than about 10 RE would be considered the global tail reconnection. So when this happens, you essentially have a wall of plasma get ejected across Y, which then breaks up into individual bursty bulk flows as it propagates towards the Earth. But testing and validating which one of these situations is actually happening using in-situ observational data is actually really tricky. And that's because a satellite can inherently only be in one place at one time. Simulations can tell us a lot, but simulations aren't out there actually measuring what's going on. So I like in-situ data, and I'm scared of Aurora, so I'm not using that. And what I've been doing in this study is taking observations from multiple constellations that are located at different points within the magnetotail, seeing when they both detect bursty bulk flows, and evaluating the spatial separation to see what that tells us about these 3 situations here. So if we have the local and isolated tail reconnection, and we've got our MMS and our THEMIS satellites just out in the tail, a relatively large distance apart in Y, we will not be able to simultaneously observe the bursty bulk flow with both of these 2 satellites. Our BBF is only a couple of RE wide, and the 2 satellites are too far apart to both see the bursty bulk flow originating from a single localized X line as it propagates towards the planet. Our MMS and our THEMIS satellite will only both be able to see a bursty bulk flow around the same time when they're very closely aligned in Y in this localized scenario. However, if we have bursty bulk flows originating from multiple points in Y, it's possible for our satellites to actually be very far apart in Y and both detect bursty bulk flows around the same time. That's true for the patchy reconnection scenario, so multiple localized X lines, and also, going the wrong way, for this global reconnection scenario. So when we have both multiple localized X lines and one very, very big X line that extends a long way along Y, it's possible for both MMS and THEMIS to be spatially separated by large distances in Y, but both see a bursty bulk flow around the same time. So using these timing correlated observations of bursty bulk flows between our 2 constellations allows us to distinguish between local and isolated reconnection sites versus either of those 2 tail-wide situations, the patchy localized one versus the global tail-wide scenario. So the first thing I had to do for this study was to actually identify my bursty bulk flows. I did this over an 8-year time period using both MMS and Themis data. The first thing that I looked for when I was identifying my bursty bulk flows was checking that the satellites were actually out in the magnetotail. And this was based on spatial parameters visualized by the black lines over here with the gray dots showing the MMS location. And then if our satellite was inside the magnetopause model, further away than this circle at 8RE and also tailward of this vertical line, we went and checked the plasma criteria, the plasma beta, to see if it was actually also in the plasma sheet. So the green dots on here are showing MMS's location when it was in the plasma sheet over an 8-year period. If our satellite was in the plasma sheet, we went and checked the velocity data and evaluated if there were fast plasma flows. We required that the velocity magnitude was greater than some location-dependent threshold, and also that the velocity was primarily in the x direction, so going majority tailward or majority earthward. When all 4 of these conditions were satisfied, it triggered the algorithm and said, hey, there's something happening, and then we defined our start and end times to be when our velocity was above a third of this threshold velocity here. This is still a work in progress. I have applied this algorithm to MMS, but doing it with Themis is tricky and a work in progress. So the results I'm showing you here with the Themis data were obtained using a slightly older version of the algorithm, where I didn't check the plasma beta, so our satellite was in the magnetotail, but potentially not in the plasma sheet. And we also didn't check the x component of the velocity. So it's possible the plasma flow that I was looking at with the Themis events could be majority in the y or z directions. But over a very long time period, 8 years for MMS, 7 years for Themis, because I didn't go back and add another year of data, MMS saw about 2,000 bursty bulk flows. I'm 100% certain that the vast majority of these are bursty bulk flows. I've done very thorough spot checks. And then the Themis detections with their older version of the algorithm, which needs updated and very thoroughly checked, saw about 3,000 each. So we have lots and lots of data to play with here. And what I had to do to evaluate that spatial separation question was to take all of these MMS detections and see how often Themis was actually in the magnetotail during these events. So how often Themis was actually capable of making a timing correlated observation of a bursty bulk flow. And that gave us about 400 events to play with, and roughly a third of those had Themis make a timing correlated observation, timing correlated detection of a bursty bulk flow. So I didn't place any spatial conditions on the Themis satellite other than that it had to be in the magnetotail. So I took these 140-ish events and calculated the spatial separation in y between our satellites. And that gave us this histogram. The bins here are 3RE to correspond roughly to the size of the bursty bulk flow. But this doesn't tell us much by itself. We also have to account for the average separation of the satellites while they're both in the tail. So this is also the spatial separation in y of MMS and Themis at times where MMS detected an event, but Themis was in the magnetotail. So not necessarily also detecting a bursty bulk flow, but capable of seeing one. So we take this first histogram, divide it by the second histogram, and it gives us this, a normalized spatial separation when both satellites, MMS and Themis, have a timing correlated observation of a bursty bulk flow. And the important thing about this is that it's quite flat. Our satellites can be 10 RE apart, 20 RE apart in the y direction, and both see a bursty bulk flow around the same time. And that is not consistent with a single spatially localized magnetic reconnection site. If there was only one fairly small X-line active in the tail at a time, we would expect to have a massive peak at small separation distances in y and absolutely nothing outside of that. We definitely wouldn't be 20 RE away in y and still seeing timing correlated bursty bulk flows. So this tells us that our local and isolated picture is unlikely to explain the events that I was looking at. What's most likely in these situations are either of these two tail wire configurations. either the patchy condition or the global situation. This does have a couple caveats. I am using an older version of my thermos detection algorithm, and getting that updated is going to be really important. The major roadblock I'm having, which I'd appreciate a hand with if people here are thermos experts, calculating the plasma beta from thermos data is something I've been having trouble with. I need to figure out how to combine the ESA and the SST observations to get the ion plasma pressure and also do that efficiently over an 8-year time period. So if someone could email me, catch me in a coffee break with help on how to do that, I'd really appreciate it. But I will wrap it up now because I see Harry staring at me. So thank you, and I'll happy to take any questions.
So, quick question, and maybe you said this, so I apologize if I missed it, but did you, for your events, do they just sort of occur at all times, or did you categorize them with respect to substorm phases or anything like that?
No, this is just every single event that was detected by MMS. I would really like to look at substorm phase, solar wind driving activity, stuff like that, but it's future study.
Got it, very nice.
All right, very nice job, Harriet. First, I was wondering why you chose a 30-minute separation time, because I just did some quick math, and it's if it travels at 400 kilometers per second from 30 RE to 12, that's about 5 minutes, or if it's 100 kilometers per second, that takes about 20 minutes. Do you want to comment on that?
Yeah, the main thing I was worried about there was if we had MMS away out at 30 RE and thermos was much closer in, that we're 100% sure to catch a single bursty bulk flow as it propagates in. It was probably a bit overly conservative, so I do want to play around with that timing separation and make sure these results still hold when we have a smaller DT value.
Okay, and then the other question was, we can talk afterwards too, but did my email help you at all with the beta calculation?
Oh, I didn't see that you replied to my email.
Okay.
Thank you.
All right. Well, let me know after you've had a chance to look at it.
Awesome, thank you.
Sure.
Super quick question if I can, because I think this is related. Do you make any attempts to separate just global convection flow with localized flow bursts?
What do you mean by globalized convection?
You could just have broadly distributed in the y direction convection towards the Earth, which wouldn't necessarily be the same thing as, for example, bubbles coming in sporadically from reconnection.
So
I know it's a somewhat distinct question, but...
Yeah, I think my algorithm criteria should filter out those events, but I did also go through and very thoroughly check the MMS observations. I think I looked at probably 1,500 of the 2,000 events that were detected and just eyeballed them. So I don't think I have the global convection still in there, but it would be helpful if you have suggestions on criteria I could also look for to make sure I don't have them.
All right. Yep. Thank you.
Thank you.
Yeah, my question's kind of related to Christine's. The 30 minutes seems like unreasonably long for what you're trying to do. Typical flow bursts last for, 10 minutes or something like that. You also have to recognize they move azimuthally. You can see that in the ionosphere a lot. But they do have a tendency to occur multiple times over a course of 30 minutes or so. So if you decreased your time interval to 10 minutes or 5 minutes or something like that, and your number of cases dramatically decreases, that would rule out number C, which I think is ruled out scientifically, but that's another issue.
There are still simulation studies that are showing this sort of tail-wide thing. I might have drawn this a wee bit longer than the simulations show, but there are simulations that have come out recently-ish that show at least a 10 RE long X-line.
Yeah, but you could kind of rule that, in or out, I guess, by shortening your time interval to, say, 10 minutes and seeing whether that changes your statistics. And if it changes your statistics a lot, that would mean that it's obviously B, where that doesn't necessarily mean they're all there at the same time, but they're coming and going, several of them within 30 minutes.
Yeah.
So that,
Yeah, I
that
do
would sort of
definitely want to
answer
play
that
with
one for you.
that time window once I've nailed down the themis identifications. But it's like one problem at a time.
Yeah, so it would be easy to change it to 10 minutes, wouldn't it? Or
It would be straightforward in the code, but I don't think it's sensible to continue doing more analysis when I haven't got internally consistent MMS and themis detections.
Was there another question?
Thanks, Harriet. I just wanted to ask if you had any thoughts about how you would then go about distinguishing between these two remaining cases. Would you need to do a different study to do that?
Yeah, I think that would be tricky, and I think it would need more than 2 satellites to distinguish that. But if we have the case, I don't think I can draw on here. Okay, imagine we have like MMS1 right here detecting a bursty bulk flow. Then we've got themis A in sort of the gap between these 2 reconnection sites, and maybe themis E, an RE or 2 further away, also seeing a bursty bulk flow. I think that would help diagnose the patchy versus global situations. But that would need to be careful case studies. So yeah, also future work.
All right, thank you, Harriet.
Thanks.
Next up is Catherine Davidson.
Okay. Hi, everyone. I'm Kat Davidson. I'm a new postdoc with Toshi's group at Boston University. And today I'm going to be talking about investigating pre- and post-onset ionospheric flow channels. So as has been discussed in these sessions already, ionospheric flow channels have been shown to play a crucial role in magnetosphere-ionosphere coupling sequences. This example from Lyons et al. 2022 shows the Themis all-sky imager data in this top panel, and then the overlaid SuperDarn flow vectors in the bottom panel. In the middle, we see our substorm onset and then our subsequent expansion phase. And in the flows, we see prior to onset, these flow channels beginning to make their way towards the growth phase arc. And the onset occurs when these flows intrude upon the onset arc in the second panel here. And then interestingly, they also saw that these flows continue into the expansion phase, suggesting that these flows may also contribute to substorm expansion. However, more evidence is still needed to confirm whether or not these ionospheric flow channels lead to substorm onset. And it's also largely unknown what contributes to the size and duration of the substorm expansion phase. So that brings us to our 2 motivating questions for this work. Characterize the influence of the intruding ionospheric flow channels on substorm onset location, and determine the role of ionospheric flow channels on substorm expansion. So to do this, we use Themis all-sky imagers, T-Rex RGB cameras, and then the high-resolution SuperDarn flows. These flows are obtained from the spherical elementary current systems method, and this gives a spatial resolution of up to 0.5 degrees and 1.5 degrees in latitude and longitude. So this is an example of the data we'll be using. We see the all-sky imagers data in grayscale, and then the T-Rex RGB, this is actually the green line, data in green scale, and then we have our SuperDarn flows overlaid on top of these images so we can observe the impact of these ionospheric flows on substorm phenomena. So I'm going to be talking about 2 substorms in one night today. So the first substorm was in the Rabbit Lake camera around this location here. And then the second substorm was in the Inuvik camera around this location here. The first substorm was substantially weaker than the second substorm. We see less spatial expansion, and we also see a smaller geomagnetic disturbance as well. And what you'll see in this video are 3 different things. First, you'll see that the pre-onset flow channels do connect to the growth phase arcs prior to onset. So for the first substorm, we'll see the flows heading towards this Rabbit Lake area, and then the second substorm, the flows divert and head towards Inuvik and trigger the second substorm. And then the expansion duration will also correspond to the presence of ionospheric flow channels. So both of these substorms show a stepwise-like expansion of the substorm. And these steps of the expansion correspond to whether or not we're getting strong flows into that region. And we'll also see that the expansion width and intensity correspond to the polar cap flow channel width and speed, respectively. So the second substorm, which is much more expansive and stronger, will have a broader and more intense polar cap flow channels going into that region. So I'm going to start the video. And yeah, you'll see these flows coming in towards Rabbit Lake. Our onset is slightly off camera here, but we see those strong flows heading into that region. And we get our first bit of expansion. The onset begins to expand across this arc, and we get those flows going into that region. And our expansion continues. And then we get a brief diminishing of the flows into expansion and a decrease in expansion, and then once those flows continue, expansion continues westward again. And now, once the flows stop, then the substorm ceases, and we get our recovery phase. And now we jump an hour ahead to prepare for the second substorm onset. And you'll see these flows start to divert up in the polar region towards Inuvik. There's a pseudo breakup there, and you see these flows coming in and connecting to this growth phase arc here. And now we get those flows really diverting towards Inuvik, really strong flows, and a really broad expansion here. And our expansion continues with the presence of these strong flows. And then once these flows diminish, we also see the substorm cease, and we get our recovery phase. You can see no more expansion, no more strong flows. And this evidence is also shown by the kiograms. So this is a kiogram of the first substorm in Rabbit Lake and the second substorm in Inuvik. And these flows are the blue color shows the equatorward flows going towards that onset location. And these are the flow vectors at the same location as the cameras. And the green box shows the latitude range of the cameras, so you can see those flows intruding into the region. And so we see that these onsets are preceded by the equatorward flow channels coming in here and here. And these two images are in the same color scale, so you can very clearly see that the flows going into the stronger secondary substorm are a lot stronger and have a lot longer duration than the first substorm. And we also see this stepwise expansion in the Inuvik substorm especially. Right around 9 UT, we get this recession of the substorm and then continuation. And we can also see a gap in the strong equatorward flows into that region. So in conclusion, we have shown evidence that intruding ionospheric flow channels originating from the polar cap heavily influence the substorm onset location. We had 2 substorms in the same night where the polar cap flows were directed towards one camera and one onset and then diverted towards another camera for another onset. And the continuation of the substorm expansion directly corresponds to the presence of strong polar cap flow channels. So as soon as we lost our polar cap flows, we also had a diminishing of the substorm expansion phase. And the intensity and spatial extent of the substorm expansion corresponds to the magnitude and width of the polar cap flow channels as well. So we had a stronger substorm for more intense flows. Obviously, a statistical investigation is needed to fully characterize these relationships between the flow channels and the substorm progression, and that's something that we're working on now. And if you want more details and more events, please come to my poster tomorrow afternoon.
Any questions? So I have one, I'm trying to think how to phrase it properly, but it's this first bullet point here. Basically the substorm onset location, right? You have those two different spots. How separated are they in MLT when substorm onset occurs? Do you see what I'm saying?
I'm not sure I understand your question, like how...
Well, because the two substorms are like an hour or two apart.
Yeah, so I think I understand your question, and the flows for the first substorm were much closer to midnight, whereas I think in the second substorm it was more so like an hour or two away from magnetic midnight, so...
And is that an hour or two on the dawn side or the dusk?
Dusk side.
And that's the stronger substorm?
Yes.
Okay, very nice.
Hi, Kat.
Hi, Shannon.
Interesting talk. I like the maps. Very interesting. But what I find the most interesting is that, okay, maybe there's a correspondence between we have this flow channel and then we have the substorm expansion, but what your work is showing is that the intensity or the velocity of the flow channels is related to the intensity and spatial extent of the expansion. So can you explain, I mean, as best as you can, how those two things could be related?
Yeah, I think what that has to do with is continuing to feed the instability that like triggers substorms and substorm expansion. So you're getting more fuel in the fire, basically.
Okay.
Okay, thanks very much.
Okay, thank you.
Good afternoon, everyone. I'm Wei Qingsun from UT Dallas, and thanks for being here. Today I will talking about substorm magnetotail dynamics and low altitude insights from elephant and survey observations with RCM simulations. The low altitude spacecraft cross the low altitude projection of the entire inner magnetosphere within several minutes and provide us a unique opportunity to trace the dynamics in the Earth's magnetotail during substorms. These figures shows typical elephant observations before the substorm growth phase and during the substorm growth phase. These panels shows the electron flux versus the centered magnetic latitudes, where the magnetic latitude equals to 0 represents the transition region between the outer radiation belt and the plasma sheet. From top to bottom, these panels shows the trapped electron flux, the precipitating electron flux, and the ratio of precipitating to trapped electron flux. One clear feature is that almost the entire plasma sheet region shrinks during the substorm growth phase. And in this lower figure shows the superposed epoch analysis of elephant flux measurement during 34 substorm events. These panels show the electron spectrum during the preceding stage, growth phase, and the expansion phase. It confirms that During the substorm growth phase, almost the entire plasma sheet region shrinks into a small interface region. And here is the interpretation of elephant observation. As we can see in this cartoon, it shows the magnetic field reconfiguration during quiet time and during the late thinning stage. So the elephant observation is interpreted as the magnetic field reconfiguration during the current sheet thinning. So here in this study, we use the Rice convection model, which assumes Fourier isotropic distribution to simulate the electron dynamics in the plasma sheet region. And these two panels shows the comparison of magnetic field configurations in the XZ plane at the start and end of the substorm growth phase. The background color contours shows the BZ distribution, and several magnetic field lines are traced from different equatorial positions at time 0 to the end of the substorm growth phase simulation. For example, the magnetic field lines whose footprint locates at L shell equals to 7.6 was stretched to L shell to 19.4 at the end of the 2-hour substorm growth phase simulation. This movie shows the simulated electron spectra along midnight. And since RCM assumes Fourier isotropic distribution, we can't directly infer the isotropic boundary using the ratio of the precipitating to trapped flux and what we did in the elephant observation. So here we use the ratio of magnetic field curvature radius to the particle georadius as the indicator, where this ratio equals to 8 means the transition region between the outer radiation belt to the plasma sheet region. As we can see in this movie, and the time progresses, the latitudinal range of the plasma sheet region shrinks from about 3 degrees to about 1 degree here. So in one word, in this work, we test the hypothesis that the shrinking of the low altitude projection of the plasma sheet can be attributed to the magnetic field reconfiguration in the magnetotail during the carrot sheet thinning, and shown in by RCM simulations. Following elephant observation during substorm growth phase, another low-altitude spacecraft survey revealed that particle acceleration during the expansion phase can produce relativistic electrons up to several MeV. And this figure shows the typical survey observation from low altitude. The upper two panels shows the electron spectra during the substorm growth phase, and the lowest one shows the electron spectra during the substorm expansion phase. There is a clear newly injected electron population distinct from the outer radiation belt. And similarly, we use the Rice convection model to simulate the electron acceleration during the substorm expansion phase. The upper panel shows the 300 to 500 keV electron distribution in the equatorial plane, and the lower panel shows the electron spectra along the midnight direction. We initiate a bubble at 1 hour around midnight to simulate the electron injection after substorm onset. As we can see in this movie, there is a flux enhanced region after substorm onset due to injection, and in the electron spectrum, the latitude range of the plasma sheet expands and filled with electrons of several hundred keV here. The lowest finger shows the time record when the simulation shows similar structure to the survey observation. We extract the flux energy profile and the peak flux position and the tail position of the injection structure, both in the observation and in simulation. And here is a comparison. The solid lines are from observation, and the dashed lines are from simulation. They match well with each other in the plasma sheet region. And here is the summary. In one word, in this work, the comparison between the survey observation and the RCM simulation demonstrates that the substorm electron energization in the plasma sheet can produce larger than 1 MeV electrons, primarily through the adiabatic heating associated with the earthward transport. Oh, that's all. Thanks for listening. Any questions?
I have one quick question about the RCM Survey comparison here.
Yeah.
How sensitive, I mean, do you know how sensitive it is to the location you choose for your bubble injection? In other words, can you like optimize bubble injection location using the survey data?
Yes, the survey data we choose here is mainly around the midnight, so we initiate a bubble also around the midnight here.
But Survey's, wait, where is Survey located in the
Yes.
RCM?
Yes, the MLT is.
Oh, I see.
Yeah.
Oh, okay, I see, that makes sense. Thank you.
For your elfin multi-epoch analysis where you overlaid the
Here?
back one slide.
The observation?
Yes. Yeah, for the superposed epoch analysis, were they all taken, were those all slices at the same MLT, or did you bin it by a certain width?
Yes.
Do you know the width of the MLT of those 34 observations?
Yes, we didn't show here, but it's just in the night side around midnight.
But do you know, like, if did you slice it like 2 MLT or 3 hours MLT?
I didn't remember the exact criteria, but it should be maybe within 2 MLT here.
Okay.
Yes, thank you.
I would just say if you slice on midnight, it might shift what these images look like, because you'd expect the thinning to be heavier, to be asymmetric.
Yes.
So I would just be aware of what, where you're slicing in MLT and how wide your bin is for those when you're doing the multi-epoch analysis. But good talk.
Yeah, thank you.
Any other questions?
The results are really clear and really interesting, but I just wanted to make a comment about the terminology. So you mentioned that entire plasma sheet collapses to a degree or 2, but from the optical measurement point of view, the oval very rarely gets to that narrow latitudinal length. And your measurements are limited to like 100 kV and above, and there are lots of low energy population that you can't measure. They can extend to perhaps wider latitude range. So just be careful that this is just based on the high energy particle point of view.
Yes, thanks for your suggestion, Toshi.
Okay, let's thank our speaker.
Yeah, good afternoon, everyone. I'm Xiaojia Zhang from UT Dallas. Today we'll be talking about our recent work on looking at the electron acceleration in the substorm magnitude tail from low altitude measurements. First of all, let me briefly mention that we will be using some relatively non-conventional data set for this study. They specifically will be using these 2 low-altitude CubeSats, which are originally designed for the radiation belt dynamics. And also we'll be using this energetic particle detector to look at how efficiently electrons can be accelerated during the substorm magnitude tail. Yeah, specifically focusing on this mean magnitude tail region beyond 10 to 15 RE, as marked here. And before we talk about what we found out at the low altitude projection of the equatorial magnetic tail, let's look at what the equatorial mission has told us before. So specifically, I've shown here 2 recent studies dedicated to those events that was specifically searched for in the earthward side of a near-Earth reconnection. So shown here on the left are these examples of the electron acceleration spectra, or spectra of the accelerated electrons. On the left is from MMS, which shows this, but we probably cannot read the labels, but this is phase space density versus energy, or flux versus energy. The left one is from MMS, and which shows the upper limit of this electron at about 500 keV, and the second event on the right shows an upper limit of the electrons up to about 700 keV. But as we all know that this apparent upper limit of the electron acceleration might not be completely physical, just because these magnetic tail emissions are the detectors on these magnetic tail emissions are really relatively limited to those sub-relativistic electrons with relatively low sensitivity to those high energy electrons above 500 keV. So that's why in this study, we will be using those energetic particle detectors from the low altitude CubeSats to probe those electron acceleration in the equatorial magnetic tail. And in a nutshell, I can tell you that we have found out that this upper limit is actually can be much higher in the substorm interval. So shown here is one such example observed by Alphen spacecraft. So let me walk you through these measurements first of all. So Alphen, as we all probably know, that this is a low altitude CubeSat that traverses the low altitude projection of the entire magnetic tail really fast within about 5 to 10 minutes. So shown here is the one outbound trajectory from Alphen, from about outer radiation belt to the plasma sheet region. And one advantage of this CubeSat is that can simultaneously probe those locally trapped versus the precipitating particles. So that's why we can use directly this precipitating to trapped flux ratio to identify those isotropy boundary which separates the outer radiation belt from the magnetic tail. That's the first step we need to do in order to examine the electron acceleration in the magnetic tail. So shown here is such example. On top panel is just the locally trapped electron spectra, and the second panel here is the trapped to precipitating to trapped flux ratio. So first of all, from this second panel, we can see this sort of a dispersive signature of the electrons, which marks those isotropy boundary for electrons. Because it's electron measurements, which I forgot to mention. So poleward of this isotropy boundary, we are encountering this magnetic tail region, as marked by this black arrow here. So we can see that these trapped electrons are dominated by those relatively low energy electrons in this detector, below about 300 keV, which agrees with the magnetic tail emission in the equator. And you can see embedded within this background, we have this jumps of the relativistic electron flux with more or less isotropic distribution, as indicated by this reddish flux ratio. So these are the electrons accelerated in the magnetic tail, probably due to the inner Earth reconnection. So that's why in this event we can see that this, if we agree that this is electron acceleration due to the reconnection, this can give us the upper limit of electrons up to about 5 MeV, which actually approaches the upper limit of this detector. And also the fact that this relativistic electron burst is very much separated from the outer radiation belt, just indicating that it's most likely locally accelerated electrons. And of course, this is not the only example we see at Alphen. Here shows another 6 examples. You can see that during all of these examples, we see this relativistic electron burst in the magnetic tail region, powered from this isotropic boundary we identified from Alphen. And one thing to point out is that all of these bursts are observed at some elevated AE level intervals, but not necessarily that very high AE. So you can see majority of the events have relatively moderate AE levels, indicating that not necessarily it requires strong substorm activities. And since Alphen sort of suffers from saturation during this kind of strong acceleration events, so that we cannot exactly extract the particle energy spectra out of it during these events. So that's why we use another measurements from Sorby CubeSat, which can give us directly this energy spectra. But on Sorby, that we use a different method to identify the isotropic boundary, which we rely on the nearby NOAA or POST satellite in conjunction with the Sorby, so that in summary, that this solid dashed line or dotted line marks those isotropic boundary inferred from POST satellite. So forward of which we encounter this magnetotail region, we can see that in this event that Sorby also captured this relativistic electron burst exceeding 1 MeV in the magnetotail region, which agrees with the Alphen observation. And also that we can extract the energy spectra in this magnetotail around this relativistic electron burst interval and compared with the summit observation in conjunction with Sorby during this event. We can see that this naturally extends the energy spectra observed by summits in the equatorial magnetotail, confirming that this indeed is likely in the magnetotail region, but it's just we captured much higher electron acceleration in the low altitude. So what we did in addition is that we can feed this power, the energy spectra of this electron burst from multiple observations or multiple events in Sorby, so that we use this kind of combination of the power law and exponential function and get this empirical alpha index in the power law to be in this range. And also the fact that this E0 is greater than 500 keV just indicates that this energy spectra are dominated by a power law spectra. So that's all, since I'm exceeding the time. So I will just list the summaries here. Thank you.
Any question?
Very nice talk. So when I look at those Sorby observations, it looks very much like precipitation bands that SAMPEX, I think, was the first to identify. And I'm wondering, do you think that precipitation bands could be this and really are actually in the plasma sheet? Mm-hmm. Or is there something different about them? I mean, the first one you showed was further out, I think, but these look a lot like bands. So I was curious what you thought about that.
Oh, okay, yeah, thank you for this. Of course, I understand the concern because Sorby has a lower energy limit in this detection of about 250 keV. So that's why we don't see this background population in the plasma sheet, so that we cannot clearly distinguish it from the outer radiation belt. But you can see that here we overlay the flux contour, so we can see that this is clearly the outer radiation belt, and the fact that this burst is relatively far away from this radiation belt population just indicates that it's more or less separated from the radiation belt. And also, I didn't mention that we checked this spectra of the electron burst in the Sorby. In comparison with this radiation belt region, you can see that it exhibits the distinctly different spectra. So this radiation belt region has this characteristic exponential distribution, but this relativistic electron burst in magnetotail actually exhibits this power law distribution. Giving us
SAMPEX, we couldn't see that because they're just looking at greater than 1 MeV. I'm just curious. It might be interesting if you haven't done it already to look at the local time distribution and other things to see if maybe bands actually were this all along and we just didn't know that.
Mm-hmm.
Thanks.
Okay. Yeah. Thank you.
Hi. Have you given any thoughts on what acceleration mechanisms might be
Yeah, that's a good question. Thank you. Yeah, we are we are speculating that this is related to the initial acceleration due to the near Earth reconnection, and as these electrons are convecting earthward, right, they got additional acceleration due to either the waves or due to this adiabatic heating, such as Fermi acceleration or beta child acceleration. But this is still pending confirmation from simulations. Yeah.
Cool. Thank you.
Yeah, Hyunju asks a related question online. She asked, well, what mechanisms make the energetic particles in the tail? Are they mostly trapped or precipitating particles?
Mm-hmm. Yeah, so just to elaborate what I just responded to the previous question, so I think this, not that I think, from alpha observations, we see that these bursts are actually corresponding to more or less isotropic flux, indicating that these are indeed precipitating particles from the magnetic tail. Yeah, because as we expected that the magnetic tail is dominated by magnetic field curvature scattering, so most of these energetic to relativistic electrons will be very efficiently scattered and precipitated.
All right, very interesting. And do you know by any chance when these occurred relative to the onset of the substorm?
We didn't specifically check this because we only have like about 20-ish events.
Okay.
But like, yeah, we can check this in the next step, yeah.
All right, very interesting. Thank you.
Thank you.
Are the power law indices that you got, are they sort of, if you imagine them as a distribution, are they peaked around a value, or are they really just kind of like anywhere between 1.5 and 4.5?
Yeah, I don't think that there is such a distribution, with the most probable alpha. Yeah, so most likely this is just a range that we examined. But of course, this is based on limited statistics.
Hi, I wanted to follow up on the comment that Robin made, that you do see this nice, clear distinction between the main radiation belt and these precipitation events.
Mm-hmm.
But with the LEO measurements, you're not only seeing a radial gradient, but also the size of the loss cone. As you get into the more tail-like field lines, the loss cone gets tiny, 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 tiny.
Yeah.
And so if you had a precipitation event still in the outer radiation belt, that is creating more field-aligned particles, then that might be superimposed upon this effect of the narrowing of the loss cone. Do you see what I mean?
Not exactly.
So what you could do is if you look at the size of the loss cone as a function of radial distance,
yeah.
then as you get from the more dipole field lines into the more tail-like field lines, it shrinks from maybe a few degrees to a few tenths of a degree. And so your fluxes will drop very precipitously. And then if you add on top of that a more field-aligned population, that could still be in the outer radiation belt, not in the plasma sheet.
Yeah, I see your point, but the fact that why we are confident or why we tend to believe that this is indeed a plasma sheet or magnetotale region, just because that first thing that we can see that from Alphen, this is relatively far away from the radiation belt region where we see this typical anisotropic distribution, because this clear dispersive signature of isotropic flux actually tells us exactly where IB locates during each of the orbits, right? So that this relativistic electron bursts we observe are actually very far away from the radiation belt region that we see at Alphen in situ. But of course, in Serbi, this is we can only use nearby post satellite to infer the IB location. Yeah, I see your concern, but that's what mostly we are inclined towards. That because the fact that these bursts are far away from the radiation belt core region and also exhibit different energy spectra gives us confidence this most likely a different spectra or different population other than the radiation belt. Yeah, but we can discuss about this.
Yeah, you might just look into the loss cone, the size of the loss cone, and see how that might contribute.
Okay. Yeah. Thank you.
Okay, let's thank our speaker one more time.
we go. All right. Hello, everyone. My name is Vincent Ledvina. I'm a second-year PhD student at the University of Alaska Fairbanks. My advisor is Don Hampton, and as you can probably see by the template, I'm doing an internship at the Aerospace Corporation with Christine Gabriels, and just want to say thank you for the conveners for allowing me to present here today. I'll be talking about auroral beads in my presentation here, specifically statistical properties of auroral beads. And here's just a quick outline of my presentation. I'll first get into a little bit of background about what auroral beads are. I'll go over our research questions, a case study, the methodology that we're using for a statistical study, and then some very preliminary results. So this is probably not new information for most of you, but just want to quickly kind of give us some context for what auroral beads are. Just a kind of general definition, they're quasi-periodic optical waves, but they really just look like sort of a string of pearls, and those pearls would be like an individual auroral form or like brightening, and then that string, guiding the pearls is a pre-existing auroral arc, for example. And they almost always appear right before auroral substorm expansion onset, but they can also appear before pseudo-breakups or non-substorm events. These beads form in the equatorward portion of the growth phase aurora, which when you map that out to the magnetosphere is sort of in that transition region. They typically have lifetimes around 30 to 90 seconds, and their brightness increases exponentially with time, which just kind of lends itself to indicate that it's a linear stage of a plasma instability. And it's likely associated with some sort of ballooning mode. And on the screen here are just two figures that I really like. So the top one is kind of showing where these beads may map inside the magnetosphere. It's a slide from Babu et al. 2024, and they examined an event which transitioned really well from beads to vortices to poleward expansion, and you can see where that maps sort of into that inner magnetosphere area, and also hinting that it may be some sort of shear flow ballooning mode instability. And then on the bottom is a sort of three-panel figure showing auroral beads in a polar orbiting satellite field of view, as well as from the ground in Themis ASI, which is what I've been using, and from the ISS. And so our research questions are, how much can auroral beads help us understand the onset mechanism of substorm expansion? Specifically, do auroral beads preceding pseudo-breakups and auroral beads that precede substorm expansion have the same properties? And whether or not, if they appear the same, are they necessarily required then for substorm expansion phase? And then, what are the different properties between the two? And the movies that you're seeing here, on the left is an auroral bead event before a pseudo-breakup, and then an auroral bead event before a substorm expansion here on the right. And then these are just on the bottom. I just froze two frames to show you that, if you just saw these two pictures of auroral beads right next to each other, you may not be able to know whether or not those beads were followed by a poleward expansion or just a pseudo-breakup. And so this is the same two events, just in a different sort of format. And what you're looking at is from A to D, you're looking at that pseudo-breakup event, so panels A to D moving from left to right. And then panels E to H, you're looking at that just normal kind of substorm event. And you're looking at Themis ASI, and these are just sort of the raw images that I pulled down. And then I marked where the beads are with these yellow arrows. And the panels A and E show the first frames where the auroral beads can be identified. So that's, three sort of quasi-periodic, auroral brightenings. And then panels B and F show those beads further evolved, so as they're growing exponentially. And then C and G show that transition from the linear phase, which is, those nice, evenly spaced beads, they just kind of look like little circles, to when they start to spiral around, kind of forming those Kelvin-Helmholtz-like spirals. That's where that happens here and here. And then in panels D and H, you can see sort of the outcome of those two events, right? The left one, the pseudo-breakup event, basically leaves you with no aurora in the field of view and not much poleward expansion. And then the right side, you can see a lot of poleward expansion in that classic substorm in the keogram, which you can see below. And then just want to make sure that you all are aware that these Themis ASI raw snapshots and the keograms are not necessarily the same time interval. So actually, interestingly, we had two pseudo breakups followed by the substorm. And I've been looking at beads for the last couple summers, and this is fairly common to see these pseudo-breakup events before the final expansion phase. And so what we're doing for a statistical study is actually tracking individual beads over many events. So I was looking at the Themis ASI keyograms and picking out where I was seeing auroral beads, and then noting those times down, and then going more into depth for each of those events, picking out 3 beads and tracking them through the image. So this is a really nice example where you can track the auroral beads through the entire sequence, and you can get properties like the growth rate, the wavelength of the beads, the propagation speeds, and these are just sort of our criteria here, 3+ quasi-periodic luminosity structures. You can see sort of structuring in the aurora a lot of the times, but for it to be considered a bead in our statistical study, those structures have to sort of explosively intensify. And then, and then for the substorms, right, it's really, there's a lot of different ways you can define what a substorm is, but for our study, we're actually using, there's thresholds based on like the SML and things like that, but we're actually using sort of the optical definition, which is a large poleward expansion, and then we're also looking at the neighboring Themis ASI field of views. If we see a bead event sort of at the zenith of one of the Themis ASI field of views, if that expands outside of that one Themis ASI, then that's a substorm because it's propagating sort of across the auroral oval. And so here are just some very preliminary results. We've only looked at the substorm producing beads. We have not actually compared the two yet, but that's the next step. And so far, with this sort of different methodology, we've been able to reproduce some of the results that have previously been found by other studies. So I just want to rattle off these key points here. So beads with larger growth rates evolve more quickly to poleward expansion, while beads with smaller growth rates last longer. That's in panel 6. Down here, wavelength of beads is roughly proportional to the bead velocity, and some studies have found this to agree best with kinetic ballooning interchange instability, so that's in panel 10 down here. And then beads sometimes propagate opposite to global plasma convection. So before magnetic midnight, you might see beads traveling eastward, and then after magnetic midnight, traveling westward, although we all know that the westward traveling surge, before magnetic midnight, that's sort of the global convection picture. The beads sometimes don't follow that normal pattern. And I guess the main point here is that we're using a different methodology where we're actually tracking individual beads. And so far, things are looking pretty promising with how the statistics are turning out. And the next step is just to expand this to the 2 different types of events that we have. We have 300 total bead events, and we're looking at the substorm producing beads and the non-substorm producing beads. And with that, I'll take any questions. Thanks.
This isn't directly related to what you're trying to study, but as I was looking at your pictures, are the scales of the auroral beads that you see in the all-sky camera images the same as the scales that you see from the global auroral imagers? Because it seemed to me like maybe the global auroral imagers are giving you much larger beads that are much more widely spaced than what we see in the all-sky cameras.
Yeah, that's a really good question. I think that the resolution of your imager definitely affects sort of the earliest time step, which you might be able to see the beads, and just the ability to resolve the beads. So I would agree that when you're looking at a global imager, you're maybe not seeing the very earliest points in that bead's life than if you were with an all-sky camera, for example.
Do they coalesce into larger beads?
A lot of the times, what I've noticed is that the beads, appear to maintain the same structure. They just grow larger. Oh. It really, I've been scanning a lot of these events. There's a lot of variation. So sometimes the beads, the actual, beads themselves might sort of jump around. But like in this example, you can kind of follow the beads throughout the entire event.
This is sort of an additional comment in response to Jeff's question. So Mike Henderson and I were looking last summer when I was at LANL, and you can, in some of the image data, like image FUV data, there are events where you can see beads in the image data, like the FUV data, and they would fit in, like 4 or 5 or 6 of those would fit into an ASI field of view, right? But I am convinced that the bulk of the things that you see in FUV are a different branch of the instability. Like it's like these small beads do not grow into something that's like a bead, a bead, a bead, a bead across like 5 hours of MLT. That doesn't happen. That's some other branch of what's going on. But I say lots of things that I'm convinced of, and they're not always, you know. And so, but that's something that I think that's one of the most interesting questions that is really not resolved, right, in this, and that there's clearly sometimes when the FUVs can pick up something that would be these beads, and then there's, I think, something fundamentally different, but.
So, very interesting. I was just thinking there's a very good correlation between the solar wind energy input, the solar wind driving, and the size of the substorm that follows. And so one of the things that you could look at is your beads that create pseudo breakups and your beads that create proper substorms, whether there's a correlation between the levels of solar wind driving.
Thank you.
So we've got 2 online questions. Hyunju asks whether, basically she's asking how you determine the growth rate. How do you define the growth rate for the beads?
Yeah, that's a good question. I do have a very convenient backup slide for that. So yeah, the growth rate of the beads is really tricky because, and I won't go too in depth into this, but we're doing a lot of this by hand. So we're selecting the T0 and the TF, and then we're plotting the brightness of the 3 beads over time and then averaging that brightness to get the profile, you know, of the brightness over time. You can see it's exponential. You take that, you know, log linear, you get the slope, and that's the growth rate. The problem is that sometimes when you're doing it by eye, you accidentally include the nonlinear phase. So what we're trying to do is develop a method where you can systematically rule that out, and you can actually just get the linear phase of an instability. And you can see here, this is sort of one event where you can see the classic exponential growth, and then it sort of tapers off. And when you just include the linear phase of the events I showed earlier, you get slightly higher growth rates.
So just if I could just follow up comment on this, just because this is something we've discussed a lot. I wonder whether so some of the brightening is happening during the nonlinear portion of the growth, but the way that you're doing this fit sort of presupposes that all of the growth is linear, and then you're relaxing during the nonlinear stage. So that's just a thought that we should probably discuss more, but I'm wondering if you have any thoughts on how to deal with that problem if the growth is nonlinear, since that would dominate the time for growth.
Yeah, I think there's some more work that we'll do with sort of curve fitting these different brightness profiles and sort of teasing out those different nonlinear versus linear components.
All right, and we have one more question online from Yi Shin, who asks, can the candidate instability explain the rotational sense of the beads? It's an interesting question.
That is a good question, and I don't know too much about that at this stage. However, when I go back to this figure from Babu et al. 2024, I believe this early simulation by Voronkov shows the shear flow ballooning as sort of an addition of the Kelvin-Helmholtz instability to the ballooning mode. So I think the curling part might have something to do with a Kelvin-Helmholtz-like component to that.
Yeah, and it looks like it alternates too for many of the events. The vorticity just switches. All right. Any other questions in the room?
Okay, let's thank our speaker. Next up is Misha.
Okay, let's come back to reconnection. If you know, I will discuss reconnection on thin current sheets and overstretched current sheets and somewhat empirical reconstructions. As you know, to start reconnection, we need some non-MHD process. We need to demagnetize ions or electrons. So we need the current sheets to be thin, at least as thin as the ion gyro radius. And here we have a problem. Such thin current sheets, if they thin at 10 RE, they will be extremely thick at 20 RE, where we observe the X lines, because the isotropic force balance requires that the ratio between the lobe field and the normal field should be same as the aspect ratio of the thin current sheets. And the aspect ratio of the thin current sheets with 10 RE to 0.1 RE is 100. We almost never observed such small normal magnetic fields prior to the onset. So to extend current sheets, they should be stretched much more than in isotropic models. In principle, one can arrange that using electron anisotropy. And Anton Artemyev already explored this opportunity, and they have found that electron anisotropy, at least the observed electron anisotropy, is insufficient to explain overstretching. Just to visualize you what overstretching is, as you can see in the Harris-like isotropic equilibria shown in the bottom, the field lines coincide with isocontours of the current density. In overstretched current sheets, the isocontours are much more stretched much more. I already mentioned in the previous sessions that in MHD simulations and in peak simulations with isotropic equilibria, we always have this problem. X lines appear too close to the near Earth boundary. So what happens with overstretched current sheets? Recently developed generalization of the Harris equilibrium, assuming ion anisotropy, does explain the overstretching itself. But what is the evolution of such current sheets? To explore that, we use this overstretched equilibria as a starting point in peak simulations. And we applied the widely distributed driving field to this equilibrium. What we have discovered, first of all, the X line indeed appears much farther from the left boundary. Here at 70 DIs, roughly 7 RE. Second, we discovered that the onset is preceded by the formation of divergent differential flows. So as you can see from this bottom right figure, the velocity of plasma closer to the Earth is larger than the velocity of plasma farther in the tail. So effectively, if we go to the system, which I show in the left bottom panels, if we go in the system which we subtract the background velocity to highlight faster and slower flows, the pre-onset configuration is characterized by effectively diverging flows. So plasma is turned off by the diverging flows. The topology, by way for comparison, we show here the outflows from reconnection regions. They are drastically different from these flows. Same situation we observe with configurations with accumulated magnetic flux. The evolution is slightly faster. But we also have found very surprising result when we decided to apply the same technology, the same setup to isotropic equilibria, which we believe before result in the formation of X lines too close to the Earth. And we discovered the same, almost the same results. The X line is forming relatively far from the Earth. We see in the left bottom panels similar diverging flows, and as you can see here from the right bottom plots, the diverging flows are even faster. So I would say these results are rather challenging and puzzling. We barely understand what is going on. It should not happen according to the theory, but we see it in simulations. Let me just briefly summarize these results. First of all, in conventional one-dimensional current sheets, when you start reconnection, you immediately change the topology. In the tail configuration, when you start reconnection instability, the topology does not change immediately. It requires some time to reconnect. And this is why the corresponding phenomena, by the way, they have already found in MMS observations, the so-called plasma watersheds, divergent flows in the absence of the topology change. So to make this to sort of preliminary conclusion, we have discovered that OTCS, overstretched current sheets, they appear to be more stable compared to corresponding isotropic equilibria. We believe this is largely because overstretched current sheets are essentially provided by these Spicer ion orbits, figure-of-8 orbits. You cannot just stretch these Spicer orbits because, I don't know, because they are figure-of-8s. The tail topology change is preceded in simulations by the differential or divergent plasma flows. And one more result, which may be, again, very interesting, we have discovered that the onset of reconnection in sufficiently long current sheets strongly depends on the distribution of the driving field. This is expected, but we did not realize it before. And it happens because if we check the ion thinning stability theory, you will see that we are always at the marginal stability level, especially if you have a relatively constant BZ field. We are always at the margin of the transition to instability. As a result, the details of the driving field may be critically important in determining the reconnection properties. So you may think that eventual final result of his simulations is negative. So I started from arguments that we need overstretching to explain the proper location of the X-line, etc. And then eventually we discovered that the isotropic equilibria can also provide that. Do we really need overstretched current sheets? I believe we do. And here is the result which confirms that. These are empirical reconstructions of the electric current during free substorms, and by the way, within whole cislunar magnetotail. And as you can see that the current sheets, by the way, both before and after substorm onset are overstretched. Color here shows the distribution of the current density, and you can see it does not, isocontours of the current density do not coincide with the magnetic field lines. So I would say overstretched current sheets are ubiquitous. And whether they help or resist reconnection, it remains still an open question. So basically, this is what I wanted to convey. We have found that OTCS is necessary to explain the location of X lines. Isotropic equilibria are, in some sense, they're insufficient. They are either too thick or too unstable to explain the pre-onset configurations. We see OTCS in empirical reconstructions. They can be explained by inertial effects by way or anisotropy and gyrotropy. And from these empirical reconstructions, you also can see that the most likely source or most likely mechanism of overstretching is the reconnection farther in the tail, most likely the open-closed boundary of the tail. That's it. Thank you very much.
Any questions?
Yeah, Mikhail, let me ask about the, let's say, next step, because you have this reconstructed magnetic field configuration, which seems like show you some overstretched thin current sheets. Do you think you can use this magnetic field data to derive the necessary agerotropy level, which we should finally find in the data of observations?
This is an extremely difficult question.
Mike.
This is an extremely difficult question. I tried to explain that we also know that the overstretching may be provided by some plasma inertia, so some flows. You need to carefully select your events based on slow or fast flow. We know that grow phase usually implies a weak, slow flows, but not zero flows. So the devil is in the details. We need to explore. Thank you.
Thank you.
Okay, thank you, Misha.
All right, so I have to admit that in my role as Deputy PI of Themis and Vasilis's first grad student, when I saw the topic of this session was substorm onsets and their connection from space to ionosphere, I had this huge self-imposed responsibility to give some sort of review talk on substorms and do a good job. And at 1 a.m. last night, I was like, yeah, I have to acquiesce, that's not gonna happen. I have too much on my plate. So I was really grateful to listen to Tuya's talk in the previous session, which I thought did a lovely job really reviewing substorms and the different ways that people think that it could start and onset. So that relieved all the pressure from me from having to feel like I'm going to do a good job of that. And instead, I'm going to have fun just going back down my own personal memory lane, channeling a bit of Bob McPheron, who often liked to come up and talk about the substorm stuff that he studied back a few decades ago. And so I'm going to walk through a little bit of that, where this first slide is actually one that I made in 2011 based on what Bob had made in 1999. And it is just a list of different signatures of, at that time in 2011, we were questioning we could call the substorm onset. And we already have covered this now, so I'm kind of repeating what we had previously discussed. But out of this long list of items that we could have defined as substorm onset, the community landed, I think, with consensus on using the brightening of the most equatorial arc near midnight that then expands into the poleward aurora. I'm sorry, where do I do like pointer and stuff? Do I use this? Do I use the mouse? Is that it? Okay, cool. So it was, for me, it was just kind of fun doing this, going down memory lane. And then I thought, oh, why don't I go to like the very second paper I ever wrote? It was on substorm onset timing. And I'm going to reread this paper. And I have to tell you what, I have done a pretty good job at putting off the midlife crisis that comes with leaving the early career stage, until I pulled up this paper and realized it's old enough to drive a car. So we've been having fun studying substorms for a while, and I thought, like I said, we're gonna walk through things that I have kind of learned throughout my time doing this. And so this is just a snapshot from that paper in 2009 that used Themis when it was, I'm really sucking at using okay. I'm gonna talk and try to not use the pointer because it's not working. Back when Themis was still a baby, and it was all 5 satellites aligned down the tail. And we use signatures of flows and magnetic fields to find where is the reconnection located, comparing to the different Themis satellites, similar to what Misha showed earlier with Vasilis's famous 2008 paper. And we also looked at ground-based signatures and the aurora and came up with this timing table where we put reconnection as happening first, and then shortly thereafter, the signatures of reconnection, the flows and such being seen by the two Themis satellites that were closest to the reconnection region. And then after that, we had auroral intensification, dipolarization onset, PI2s on the ground, and AE rise. Although one thing I point out is kind of what Tuya had pointed out, is that although that was the list of the timing, the times are all very close together. So she said it's often like synchronous almost. And that's kind of what I have noticed as well with the studying of the substorms, is a lot of these things happen so close together that it is hard to give like a causal relationship between them. And so at that time, though, we had said, okay, we have reconnection that then sends all this information earthward. And around the same time, my later to become friend and colleague, Emma Spanswick, was looking at this from the ground using rheometers and seeing that substorms start closer to Earth and then expand tailward. And she saw this too with some satellites in space, seeing a tailward expansion of the substorm observations, and therefore put the onset location closer to Earth, more at like that near Earth transition region around 8 to 12 RE. So kind of a tangential point that comes into the story we'll bring back later is also around the same time, one of my co-grad students was studying with Themis, observing how much magnetic flux is being transported earthward, and calculated how much that occurred over time. And that question of is enough flux being transported earthward after reconnection to accommodate all of that magnetic flux that we observed during the substorm? And we had a focus group that looked at this, and most papers came out of that focus group saying, yes, mesoscale flux transport after reconnection is adequate to explain the majority of the magnetic flux transport globally. So there was a Byrne et al. Paper and a Merkin et al. Paper that used simulations that found the total flux, magnetic flux, being commensurate, like 200 megawebers, with what had been observed in the past. And so now we're wondering, okay, well, what's going on? So then Emma and I looked at these events, one event in particular very closely, as well as some statistics with injection propagation directions. And I'm going to try and play this movie. Kind of the picture that we see in space, again, kind of follows that, where you have suddenly at the outer satellites, you see the flow burst, then it reaches the inner satellite. So these are the velocity vectors over time. And then essentially this is the idea of the flux pileup, where the outer satellites see that small little DFBs, so small dipolarization flux bundles, multiple ones over time. And then the inner satellites saw that too, but then it quickly built up into the large-scale dipolarization. And then as the dipolarization engulfed those satellites, you would see the velocity die down, because they are now the flows are being impeded from reaching the satellites. And at the same time, we were seeing the flux, the electron flux increase for the injections. But from the ground, you don't see it in that order. You see it, again, from the rheometers and from the aurora, you're seeing something that's starting what you, more in this, what would map to that near-Earth transition region, 8 to 9 RE. And what we did see, though, is in the rheometers, this tiny blip, which correlated to a streamer at higher latitudes. So in other words, it would be like that flow that would be from the tail. And so what this kind of picture says is that you can have these flows and flux being brought in and some particles, but a lot, as Tuya was mentioning with the substorms, you're talking about how is energy from the magnetic field being converted to plasma and electromagnetic energy, and it seems like that's not happening so much along the way. It happens here at that near-Earth transition region is where all of the really explosive substorm stuff is happening. Oh, yeah, that's saying what I just said. So walking a little farther into my research, more recently, we've been using the aurora to look at the energy deposition, how much energy flux is being precipitated, what's the mean energy of that precipitation, and then how much of that is happening on mesoscales, so like on the scale sizes of those flow bursts versus globally. And if you just focus on this red line here, which is those mesoscale contributions where the y-axis is percent, you see right at the substorm onset and expansion phase, which you see here from the SML index, you have a lot of contribution of the energy flux from mesoscales, like almost 80% of the total energy flux. And then that drops off right after the expansion phase, but is still an important contribution during the rest of the substorm. And that corresponds to what people have talked about, like Larry Lyons has pointed out, you have a lot of these flow bursts coming in after the onset that is contributing to the whole picture, not as much before as after. And so the takeaway is, okay, reconnection could supply the magnetic flux and perhaps energy, but how is that magnetic energy being transformed to the plasma energy and the electromagnetic energy? Clearly the answer lies in the near-Earth transition region, and that's where you're getting like the beads and the explosive onset that where all of the really exciting transformation is happening. So that's my workshop style talk where, you know, you don't need to clap, but if anyone wants to like discuss, let's talk.
Any questions?
I have a quick question if I can. Yeah, so this was a beautiful talk. I was wondering, you didn't mention, as far as I could tell, anything about the buildup of the substorm current wedge in terms of wedgelets versus the globally coherent thing. I'm wondering what you think of that and how to reconcile it with the sort of mesoscale buildup of dipolarization from these fronts coming in.
Yeah, it's a great question. It was another thing that our focus group had really talked about a lot over the years. And there were, so this gets back to what Jesper was talking about in the previous session. There's several trains of thought. One is that there are multiple wedgelets occurring simultaneously, and the contribution of them happening all at once is what's causing the substorm current wedge. Then there's the thought that something initiating near Earth causes the substorm current wedge. And then there's the idea of like these smaller like wedgelets coming in. They're not individually contributing to the substorm current wedge, but as the magnetic flux gets deposited and creates a large-scale dipolarization, which now creates gradients in the pressure that are no longer all equally pointing towards Earth, that creates that substorm current wedge into the ionosphere and out. And I think, I feel like answering that will make some people like me and others hate me, but I tend to lean more towards that like flux pile up, like that large-scale dipolarization, which is causing a divergence in the typical just dipole shape and the gradients in the pressure, and that creating then the substorm, the large-scale substorm current wedge. That's just
Okay, so in other words, you might see more of the wedgelet structure out in the equatorial plane, but then by the time you're up in the ionosphere, it's going to just appear like this coherent structure because all of those pressure gradients are just contributing to some integrated current or something like that. Is that right?
I'm actually going to back myself up a little bit because I forgot to mention that Toshi had a lovely paper that showed when you look at the ionosphere, there is evidence that both occur, as in you have a very coherent, all of the downward field line current is on one side and all the upward field line current is on the other side. It's one coherent substorm current wedge, which is like the large scale version. But he also showed an equal or more number of cases where the substorm current wedge was composed of these wedgelets. So you had multiple up and down field line current structures that were much smaller scale size. So I guess maybe I'm saying that like it could be both, and I think it's still an interesting area that we can continue to look into, and we have the EASY mission, which will hopefully, or we expect to give us even more information on that.
Yeah, all right. Thank you so much, Christine.
Hi. So I have a more general question. Since you have such a long experience in studying post-bulk flows and substorm onsets, I would like to understand, is it possible that there are substorm onsets at multiple locations simultaneously in the ionosphere, spread across local time and not necessarily near midnight?
It's a good question because I hate to ever say absolutely no because you can't prove a negative. I don't recall seeing that. I mean, we do have multiple flow bursts that can come in, but I've only ever I've seen like one spot where the onset occurred and then it expanded, kind of in every direction, but mostly westward and then travels westward and expands poleward too. But if anyone else has seen multiple ones in the same, it looks like maybe Larry has. Two? Okay, yeah? All right, so Larry Lyons says he's seen two onsets for the same event.
Yeah, so because currently I am studying some of the events where I see ground signatures of, currents and maybe rheometers as well. And they are not necessarily enhanced in the midnight, but in the pre and post midnight, maybe near dawn and dusk. And, there's always a struggle to understand whether it's just a pressure effect, it's like a convection pattern, or is it substorm? But then I've also observed THEMIS observations in the post-midnight and in the pre-midnight having substorm onset signatures. So I don't know if they're related, it's just arbitrary, so that's why I was looking for an answer, yeah.
Okay, thanks. Yeah, I'd have to see the data. We could sit down and look together sometime if you want.
Christine, thanks. Very interesting talk. And yeah, it's my memory too. I would like to remind actually everybody about very old results published by Nagai in 1982, if I'm correct. It was a statistical study of geosynchronous signatures of dipolarization seen on geosynchronous. It's very interesting what he showed, that dipolarization starts in very narrow interval around 23 MLT and spreads in both directions, dawn and dusk, within next 20 minutes, basically with the same speed. dawn and dusk. I wonder if now we understand these results. What do you think? Do we understand what's going on? Maybe it's a question for everyone in the room.
I guess it depends on how far into the picture you're asking, do we understand? Because my impression is that there is still some disagreement as far as does dipolarizations occur because of flux pileup, where you have magnetic flux being brought in towards Earth in the pre-midnight sector at that 23 MLT that Nagai saw, because reconnection usually occurs in the pre-midnight sector, and then that grows azimuthally as that flux piles up and spreads? Or is there an instability that, due to the thinning of the current sheet, causes some explosive reaction that builds that dipolarization at that location? And I feel like there are still some people who are on either side of the fence. It'd be interesting to take a poll, I guess, like to take a pulse of the room. I'd love to hear anybody else's thoughts.
So I was going to comment on the mesoscale thing, but I'll address this question about the Nagai paper. One of the things that's very puzzling about that is the speed at which that dipolarized area expands azimuthally is much slower than the drift velocity of injected particles that we assumed came with the dipolarization. And that's very hard to reconcile. If the dipolarization is causing the injection, why is the injection wider right from the very beginning? So I think that's still a mystery. But I wanted to comment about the mesoscale versus the global scale. It reminds me very much of the discussions that we had about the storm-substorm relationship. That in some ways, Akasofa wrote down the famous equation, storm equals sigma substorm. So, by a literal definition, a storm is because Akasofu defines substorm, so the substorm would have to do that. But, as we just studied this, we realized that, no storm happens without a substorm, but a storm is not simply a set of substorms, that there are other processes, the partial ring current and all of these things. So there are both global and mesoscale processes happening at the same time. Sometimes they add up to a storm, and sometimes they don't. It occurs to me that it may be similar with the substorm current wedge versus the multiple pileup of dipolarizing flux bundles.
Yeah, I think that's a really great analogy to help us think about that it doesn't have to be just one or the other. Like, it's either composed of them and that's it, or it's only a global thing. So thank you for bringing up that point. I agree.
Could I just add one thing to that? So I was under the impression that a substorm is not a necessary condition for a storm, that storms can happen without substorms. Is that not correct? I thought there was like a Kamita paper. I don't know if I'm pronouncing that correctly, but...
Kamide, but
Kamide, so
every storm starts with a substorm. What happens after that, it's often very difficult to identify substorms within a storm, but every storm does start with a substorm.
All right.
Okay, let's thank our speaker.
Oh, yeah. So I'm fully aware I'm the last one standing between you and your dinners. So I will try to do what I should do. So, okay, today I'm going to talk about simulation, 3D peak simulation of reconnection spreading study. And this work is done by Sanchang Li. Is my graduate student. And what I'm going to talk about is very simple, just two cases. Case one is X line. Can you see a cursor? Oh, no. Okay, X line is spreading without a kink instability. And in this simulation, you see in the top, the boundary condition is like the way we suppress the kink instability is placing the X line at a lower boundary, so the kink cannot happen along the y direction. And in our simulation, the x is outflow direction, and the z is inflow direction. Y is the X line direction, just like in tail. So you see the time evolution here from A, B, and C. You can see initially you are looking at a XY plane, so it's basically looking from top. Okay, so it's a equatorial plane. And you see initially we perturb the X line, so it starts from the center. The initial length is roughly 30 di, and that is evolve. It looks like in the panel B and the panel C, and you see the signature of BZ is a reconnected field. And you see how it is sprayed to the outer region. And also you see X line, which is around the center, at X equal to roughly 180 di. Di is an unusual scale. So you see how it's sprayed toward the top, which is the direction where ion drift to. So because we are looking at the current sheet, so electron drifting downward here correspond to the downside, and drifting upward there, and they'll correspond to the dark side. And the key message from this slide is that you see the internal X-line symmetry developed due to this the drift of ion with respect to the electron. And you can see from this time sequence, you see the X-line spreading is roughly mainly in the ion drifting direction. And later I'm going to tell you this due to the low ion pressure from the active X-line. This is drifting, the signature of low ion pressure is also drifting upward with the ion. And here is a pretty movie. You see how it sprayed. And you can see, the upper left is, the arrow is ion velocity, and the upper right is the electron velocity. And lower left is the pressure. You can see the pressure depression as the green, okay? And lower right is the electron pressure. You can see it decrease as well. I can see that the signature spreading up, and we tell you that it's the ion pressure that is spreading up is causing the continued onset of reconnection, and therefore causes spreading in the ion direction. However, in the electron direction, you see the pressure at the lower side, okay, at the bottom of the signature is not actually green, it's red. So actually the pressure there become higher, so it's not causing the pressure collapsing, and also it's not causing the reconnection spray downward. And here is a time stake plot, okay? What we are plotting is like for you to look at panel A, okay? It's electron outflow velocity at a particular given y location and at a different time, okay? It's a horizontal axis. So you see this signature of reconnection X-line sprayed upward in the background ion velocity is the ion drifting velocity because the current carrier. And on the other side is the electron drifting velocity in the red color is a line there. And however, you see that it's not, the structure is actually only drifted a little bit downward, and then everything, the entire structure being convect to the ion drifting direction. So it would be the dusk side. So this is the message is the X-line barely sprayed in the electron side for this side. Okay, so this is a case one with a kink instability, and that we are able to suppress kink. Now let's bring the kink back by performing the full 3D simulation. Now X-line is being placed in the center of the box, and the kink is able to develop with the wave vector k in the y direction. So you can see here, very similar. You have initial X-line on the left, And also, I plot the current density in the XY plane to see the kink structure. And the later time, it will be central panel and the right panels. And you can see this formation, the spreading of the X9 is being stopped by the kinking stability. And you can the signature can be seen by the cusp shape, okay, on the top. Now it disintegrates at the third panel. So cusp is gone, and therefore indicate the fluctuation from kink instability is suppressing the X9 spreading. And then you can see from this movie, okay, left is a kink instability. You can see the fluctuation. And you can see the X9 indeed trying to spread initially, but later it just die out very quickly after the onset of the kink instability. That's it.
Questions? I think everybody's ready for dinner.
Yeah, I understand that.
Just a quick question. For your first case, could you just explain again how you suppress the kink instability? Is it just in the XY plane?
Yeah, this is one only model that can do. It does not happen in nature, and also theory is hard. And so we actually, in the bottom boundary, we are using the perfect magnetic boundary, conductor boundary. So where the E perp is 0 and the B parallel is 0. And it does fit the symmetry of the X9, so we can still simulate the reconnection process and by placing the X9 right at the boundary, because the outer boundary will basically just the mirror image of the signature inside the boundary. And by doing so, we can very smartly try suppress the kink instability.
All right. Well, thank you.
Okay.
Just before we go, we do have 2 graduate student volunteers that hopefully haven't left for their dinner yet. If you can stand up and receive a round of applause for your help. All right, thank you everyone for staying 10 minutes past the hour.